Hello and welcome back to macroeconomics. Today we're going to talk a little bit about the contraction mapping theorem. This is a very important mathematical result that is going to be important for us to establish that the dynamic programming that we're going to do actually makes mathematical sense. It's important to underline that it's not true that in your career as a macroeconomist you will necessarily be doing lots of real and functional analysis and using the contraction mapping theorem every day, unless you become a theorist, of course. Rather, again, it's to make sure that you know that what you are doing makes sense. Just as in the same way as you don't necessarily need to use econometric theory whenever you're estimating something, in the sense of deriving new estimators and such. But it's important to have a very strong foundation in econometric theory to make sure that when you actually run any regressions on Stata or SAS or whatever, that you know that what you're doing makes sense. So let's go ahead and look at the contraction mapping theory. You may recall that earlier we were looking at the following recursive problem. It was one where someone was trying to choose their future capital so as to maximize the utility of consumption today plus their future utility discounted with the factor beta. Now we're going to represent their future utility using a function v of kt plus 1. And the recursive nature of the problem comes from the fact that this too should equal the value the agent gets today. This was all subject to a constraint that consumption should equal some function of capital, the production function, plus undepreciated capital that goes forward from today to tomorrow minus capital tomorrow. This summarizes the feasibility constraints along with the capital accumulation constraint. Now, what we discussed last time was that we could suppose, even though we don't know what this V is yet, we can propose a candidate. So let's take a candidate V0, which represents the agent's view of their future value. In other words, if they have kt plus 1 left over, then V0 of kt plus 1 will take the place of this V in the future here. There's an alternative interpretation of this, which is that V0 is the discounted utility going forward of assuming a particular policy function kt plus 1 of k, which may or may not be the optimal one. Either way, let's suppose that V0 is the agent's view of the future. So what they're doing now is maximizing this given V0 by either of these interpretations. We can call this V1 of kt. So if V0 is your view of what happens in the future, if you're left with kt plus 1 capital, then V1 is what you get if you maximize now, given that future view. Similarly, we can define the following. What if instead we started with V1 as our view of the future? then we could define V2 of kt in a similar way. Similarly, we can define V3 if our view of the future is V2 and so on. You could do this as many times as you like. And that's exactly what we want to do. Now, wouldn't it be nice if we could show that the following happens? First, if there is a V such that it satisfies this equation, it must be that for that V, what you get is that when you put this in here and you start with the correct V, you're going to get V1 equals V. Notice that also means you'll get V2 equals V, V3 equals V, and so on, if that's true. So we would like to show, first of all, that such a thing exists, that there is one that satisfies this equation that we started with. It's equivalent to saying there's one that when you plug it in here as a starting point, you recover it when you solve the maximization problem. Now, wouldn't it be even nicer if we could also show that V is unique? What if there were 2 or 3 or 17 of them? That would make it difficult for us to solve a recursive problem because we wouldn't know which one we're supposed to use. And a third really nice result would be, what if not only is it unique, but for any starting V0, the limit as n tends to infinity of this process takes us to that correct V. That would be wonderful. And it turns out that we can show that. However, in order to do so, we're going to need some special methods from functional analysis, which means the study of how functions in general work. So let's do that now. In order to do that, what we need to do is look at this process of repeatedly maximizing in a slightly different way. Really what we're doing here is we're saying that this equation defines something called a functional. This V1 here is not just a function of k, it's also a function of the V0 that we started with. Think about that. In other words, what this equation is doing is actually defining another function, which is the one that takes a V0 and transforms it into a V1, or takes a V1 and transforms it into a V2. This function of functions, which we're going to call sometimes an operator, or sometimes a functional, is going to be called the Bellman operator. And we're going to call it B. So an alternative way of writing this equation is to say that I am going from this B, from this V sub 0 to another function which depends on V sub 0, which we're going to call B V sub 0. So this means we have applied the Bellman operator once. to V0, and we got this, B of V0, which is V1. Now let's take this next iteration by the same token. We can say that given V1, what we get out of here is B of V1. And notice that, of course, V1 is equal to this. So this is the same thing as saying that V sub 2 is equal to B of V1, and B of V1 is B of V0. So we've used the Bellman operator twice here. And we can summarize that by just saying that B here is squared. That just means, again, we use the Bellman operator twice, or alternatively, we went 2 times through this cycle here. This means that an alternative way of describing what we would like to find is the following. In terms of the Bellman operator. First, the idea that we want a V such that when you plug it in, you end up with the same thing, can be written as following. You want a V such that when we apply the Bellman operator to V, we get V back again. Second, we want it to be unique. That would be wonderful. And third, we wanted this condition for any value of V0 that we start with, we converge to V. That's the same thing as saying that we're applying the Bellman operator infinitely many times to V0. So we can just write this as follows. Starting from any V0, apply the Bellman operator infinitely many times, and you'll converge to V. Why is this useful? It's useful because rather than dealing with sequences of functions, now what we can do is instead focus on the properties of this thing, the Bellman operator. And that is going to turn out to be much simpler. What we're going to show is that this Bellman operator B is a very particular kind of function. What we're going to show is that there's a sense in which it squeezes the space of functions together. Think about this. Suppose you started with 2 different V0s here, or wherever. Once you apply the Bellman operator, because of the discounting, the things that you get out on this other side are going to be closer together than they were when they started, those 2 different V0s. In whatever way we measure distance among functions, are going to end up being closer together once we apply the Bellman operator to them. So if we apply it many times, we're going to kind of squeeze whatever differences we started with until we end up with a V that we converge to regardless of the point at where we began. So let's look at that now. A function that squeezes things in this way has a special name. It's called a contraction mapping. What we're going to do is define a contraction mapping and then introduce the contraction mapping theorem, which tells us that if B is a contraction mapping, then it will have the properties that we want and will yield the results that we desired. So in order to do this, we need to think a bit more broadly and start by defining this object, a contraction mapping, which could occur in any space. And what I mean is the following. Consider a complete metric space S with distance function rho. Basically, what this means is we have a space of objects, a set, which is complete. Complete means that any Cauchy sequence converges to a limit that's in the space, or any sequence of items that get closer and closer and closer together converges to something, and that something is also in the space. And what's a distance function? A distance function is a way of telling how far apart different elements of this space are. It has to satisfy the kinds of things that distance intuitively satisfies, such as it must always be positive. I can't be -1 meter away from you. I am 1 meter away from you, regardless of the direction in which I stand relative to you. And distance functions have to satisfy the triangle inequality. And what that means is that the distance between me and you must be smaller, or maybe equal, but it certainly cannot be bigger than the distance between me and your friend plus the distance between you and your friend. That triangle inequality is going to be very important later. So now consider some function t that maps from elements of S into another element of S. So it maps S into itself. A contraction mapping is a function, mapping and function is the same thing, T such that there exists some number beta strictly between 0 and 1 such that, consider the distance between any two elements of S, let's call them X and Y. When you apply the contraction mapping to both these points, you would get Tx and Ty. The distance between the 2 points after the mapping must be less than or equal to the distance between the 2 points originally times this number beta, which again is strictly less than 0 and 1. This might give you some idea that maybe this has to do with discounting, and in our context, that's correct. And this has to be true for all X or Y in our space S. In this context, we call beta the modulus. So that's all a contraction mapping is. Give me any 2 points in my space, apply the mapping to them, and whatever you end up with must be closer together by at least the factor beta. That's it. And that's the sense in which what the contraction mapping is doing is squeezing things closer together. So now we know what a contraction mapping is. Next, we want to look at the contraction mapping theorem, which is going to say the following. Suppose we have our pair big S and its distance rho, where S is a complete space. Remember, that just means that any converging sequence there has a limit that's also in there. And suppose we also have our function t, which is a contraction mapping with modulus beta. Then we get two results. One, t has exactly one fixed point v in S. That's the first result. And second, for any v0 in S, the distance between the contraction mapping applied n times to v0 and this fixed point is less than or equal to beta to the power of n times the distance between v0, where we started, and the fixed point. In other words, regardless of where you start with v0, if you apply this contraction mapping enough times, you're going to end up getting as close as you like to the fixed point. Because, of course, as n goes to infinity, this distance is being squeezed towards 0. How does that help us? Well, it means that we're going to get our meaningful value function if we can show that the Bellman operator B is a contraction mapping. Now, to understand a little more what a contraction mapping is and what the contraction mapping theorem is telling us, let's look at an example. Let's say that we are looking at a complete space S, which is nothing but an interval in the real line, let's say between 0 and some point. Let's say that's a limit big S. On this axis, let's draw that space again, because we want to look at mappings between this interval and itself. And here are the bounds for our space. I'm going to draw the 45-degree line. We'll see why in a second. Of course, any point in the 45-degree line is a point where the value on this axis, the x-axis, is the same as the value on the y-axis. Now let's take some point x here and another point y here. The distance between them, using the common notion of distance, is of course y minus x, or the absolute value of x minus y. Suppose there is a contraction mapping T. What does T do? What we're going to need is T of x. So let's say T of x is just here. That means this is T of x over here. Since this is a contraction mapping, T of x must be closer to T of y than x is to y. In other words, the vertical distance between Tx and Ty must be less than what we have here. In other words, in this space, a contraction mapping is a line, whether it's squiggly or not, that everywhere has a slope that's strictly bounded away from 1 by the modulus beta. So its slope cannot be larger than beta, which is strictly less than 1. So let's say that tells us, first of all, that t of y cannot be above the 45-degree line. Let's just say it's here. So that's t of y. The contraction mapping theorem tells us that whatever else there is about this contraction mapping t, since its slope has to be strictly less than beta, which is strictly less than 1, well, weakly less than beta, which is strictly less than 1, that means that it has to cut the 45-degree line somewhere, right? In order to avoid that, it would have to have a slope that converges to 1, but it can't do that because its slope is bounded away from 1 by beta. So it has to cross it. There would be our fixed point. And why does it have to be unique? It has to be unique because, again, in order for this mapping to cross the 45-degree line again, you would have to, again, have a slope that's going to 1 or even exceeding 1. It can't do that because its slope is bounded away from 1 by beta. So that's the intuition behind the contraction mapping theorem when our complete space is the 0s interval. Excellent. So what is the point? It turns out that there are several. One is that as long as we can show that the Bellman operator is a contraction mapping, then dynamic programming makes sense. How do we do that? Well, in our next video, we'll discuss something called Blackwell's sufficiency conditions, which are going to be satisfied in many cases and which are usually pretty straightforward to demonstrate in the case of any particular problem. Second, we've also learned that through repeated iteration of the Bellman operator, we can actually find our value function, even if we have no clue where it is. We just need to find an arbitrary starting point, iterate on the Bellman equation many times, use the Bellman operator over and over, and we can converge to the value function to any arbitrary desired degree of precision. And those are very useful results. There could be some context where maybe dynamic programming makes sense that doesn't satisfy these conditions, but in general, everything is going to work out in the kinds of problems that we're going to be concerned with. So thank you, and have a good night or a good morning, depending on where you are. See you the next time.